Hello everyone. So in this video, basically we are creating a series now. So in this series, we will be talking about the RAG, the RAG that you must have already heard with LLMs. So we'll be creating a series around RAG, then what is RAG, the demo. We'll see two type of demo, one basic demo and world real, some more complex, and then we'll create a complete chatbot with RAG, right? So what is RAG? Why do we need it basically, right? So let's understand with a basic example. So we are using LLMs nowadays, right? So let's consider any LLM. It is trained till term date, till some date. Okay. So let's say the LLM is trained till 1st January 2025. Okay. Now a major event happens in, let's say, June or July, and you are using it after that. So the LLM is not aware of those events, right? So what would happen if you ask them? The LLM will not be able to answer those, or it will hallucinate, right? But you can remove that shortcoming using the RAG. So RAG gives LLMs the memory. So it's a way which allows LLMs to search the data in the RAG, get the content from the RAG, get the relevant content from the RAG, and accordingly respond basis that data. Okay. So this is RAG, and first in this video we will be talking about we will be talking about the basic example for RAG. For RAG we are using a Milvus DB. Okay, so let's understand what is a vector DB basically. So these terms are used sort of, what should I say? They are the synonyms. What should I say? Vector DB, RAG. So for RAG mostly people are using vector DB. Okay, and in this video we are using a Milvus, which is a vector DB. Okay, and it's one of the widely used vector DB. Obviously there are others, and we can keep exploring, but this also works good, right, in productions. So what is a vector DB? A vector DB, I'll explain with an example. So you use a MySQL as structured database, right, where you store the structured database. Then there comes like Solar, Elasticsearch, which is using for text search. Vector DB is basically where you want to search on embeddings, where let's say you want to do the text search using similarity, cosine similarity, product based or basic using semantic search. For that vector DB is used. So when you store the data in high dimension vectors and you want to search that data using those vectors, then your vector DB comes in picture. Okay, Elasticsearch also do supports for this, but that's not built for this. It is built for text search. Okay, so now this setup is straightforward. I have not covered it here. You can easily find this over the internet. How do install? So basically we have not, in this video we are using a local, so you need not to install anything. You just need to install PyMilvus, and I will put the environment setup command in the description of this video. Okay, so nothing needs to be done to set up Py for the Milvus. So there are basically two ways. If you want to do hello world or some local DB, you can simply use the file-based Milvus DB, which is we are checking here. If you want to use it for production, that means you need to set up a single node or multiple node cluster. You can do this either via Docker or via standalone, which is easily available as per the documentation. Okay, so nothing has been installed for Milvus for this video. It's a file-based system, so it will create this DB once we run the command. So I will put this code also. You need not to understand this code while I'm speaking. Okay, so what I'm saying, this is I'll show you the data first. So what I'm trying to store in the data. Okay, QA raw, right, this is the file. So basically what I'm storing is I'll create a database with each element of my database will contain two entities. One is the question, one is the answer. So the question is Paris sightseeing, what can I explore in Paris, and the answer is this. Then another is about Paris food, then another is about Tokyo adventure, and something so forth, so like that. So what the idea behind this is that we have stored the Paris, Tokyo data with respect to some entities, sightseeing, food, adventure, and when we want to search, let's say what's good food in Paris, so it can give me the data of around this, right? So it can automatically fetch this question and answer pair and it gives me whatever you want to get. You want to see answer, you want to get question, that's up to you. Okay, so what we have done is that we are using Milvus. So what we have done here is we have loaded an OpenAI client. We are using the Milvus DB. Currently OpenAI is only used for the embeddings in this video. We are just getting the embedding model, because as I mentioned, we are searching basis the embedding, so we need to store the embeddings for the input for the basically our data set, and once we search it, we create the embeddings for those and then search in those embeddings using either cosine similarity or some other similarity logic. Okay, so I'll just quickly run it. So it's created a Milvus client instance and it loads an OpenAI client. I've created a .env file with my OpenAI key. Now these are some helper functions. So this is the load rows. So basically I have a queue row JSON I've shown you. I want to load this in my database. So this is just loading and creating one JSON out of it. Then this embed, it is basically given this text. I want to create the embeddings for this. And this is the reset collection. Basically, if I want to drop the collection, just this. Their consistency level here is bounded. Metric type is IP. So IP is basically inner product. It can be cosine. You can leave it for now. Consistency level we'll talk about in a bit. What is consistency level? Collection is the collection name and how many dimensions we want to create for this. What would be the size of embeddings? This is, we have mentioned 1536. Okay. Yeah, moving ahead, this is the ingest function that once we load the rows, we want to store them one by one to Milvus. So this is the function for this, and this is a search function which gets some data, and we'll talk about it later, right? So what we are doing is just first in the main we are loading rows. I'll just print it for you, and then reset the collection and then ingest the rows. So now it's, you can see running, it's loaded the rows. So one pair is this. Till where? Till here. So this is the one set for Milvus DB which contains two fields, question and answers. Right, now it's done. So my Milvus DB is created. As you can see, it is here. It's, sorry, it will not be open. So it's 7 seconds ago you have seen it's created right now. Okay, and now I can search. So let's say I give it the sentence information about Paris, and I have called the search top 3 function with this query, right? So in this, what I'm doing is I have given search parameter, metric type is IP, which is the inner product, and output fields I've told that is a question and answer, and data. Sorry, so first I've got the query. I am creating the embedding of that query. As I've told you that once we insert, we stores the embedding, and once we search, then also we need to create the embeddings. Okay, yeah. Then here I am actually searching the Milvus DB. I have given the collection, I have given the data, which is the search params is these. Okay, and these are my output fields. Okay, this is, I'm just printing the data. Okay, what is the distance, what is the question, what is the answer. Okay, now I am searching about it. Sorry, it's giving me error. Just give me one. Okay, I need, it's an indentation error. Now it should work. Now it's running. So the query is information about Paris. The first result, the answer is you can visit Eiffel Tower, this and that. Then it says try fresh question, because Paris is matching, so its distance is matching, and then it's visit temples like Saint-Sugier. We don't know what is the question here. If we want to see question, we can also see question, the actual information that came. So information about Paris, sightseeing, what can I expect in Paris? This is the answer. Then, sorry, the first question was coming this Paris sightseeing, then Paris food, then Tokyo culture, right? So this is fine. This Tokyo is coming, but because this, as you can see, score is very less here, but that can be handled. I mean, just an example, just to show you that how the Milvus works. Okay, so just to summarize it, what we have done is, we have created a Milvus DB, a vector DB, file based vector DB. Then we have a JSON file. We have stored each JSON as a document in Milvus, and then we have search on that. Then we performed a search over that Milvus DB. Okay, that's about this. Now we talked about the consistency levels in Milvus, right? So I'll just give a quickly brief over this also. So there are 4 type of consistency level. One is the strong, one is the bounded, which is default, and we have also used the default, then is the session, and then eventual. Okay, so first of all, what is consistency level? So let's say you have a multi-node cluster. Okay, so let's say there are 4 nodes and you write to one node. Will the data be available to you if you query other node or same node? So this is consistency level. Okay, so strong means yes, if you write it and you try to read the data from other node also, if you are using strong consistency level, it will ensure you will get the data. But the trade-off here, you might feel some latency because it first ensure the data is present on all the nodes, and then it will allow your search query to go through. Okay, and how does it do this? So whenever we do a query, okay, it starts a timestamp. Now this is the timestamp where queries come. Now with strong consistency level, it will ensure till that t, if the data is there or not in all nodes. Okay, so I know this is getting complex, so let's understand with an example. So at 12 0 minutes 2 seconds, we do an insertion of A. Okay, at 50 milliseconds later, a search arrives, so it pick T's. This T I mentioned, it's the current timestamp. Okay, now query waits until all writes, that is all writes till 0 are visible in all nodes. That means A will be there on all nodes, right? Because it happens before. And it insert B's after 10 milliseconds of search arriving. Okay, so at 60 milliseconds, the B also arrived. So if my query will return A, it will not return B because it will give all the result till the T's. So to summarize, strong will ensure at what point your query comes, it will ensure all the result till that will be visible in your output. Okay, bounded, it's a little trade-off, so it's a just behind now. So in strong, the T is now, right? In bounded, T is a little behind now. So obviously your nodes are in sync, so roughly there will hardly any milliseconds lag only, right? So it picks T, which is slightly below. So understand with an example. So at 12:2 again A comes. After 40 milliseconds, it insert A2. Now search arrives at 50, but it picks T at 20. So 30 ms earlier it picks T. Okay, so it has to wait only till data till this is available on all nodes, which is a highly probability that it will be done now because it has picked the T of not now but a little behind now. Okay, so no wait needed. Engine searches snapshot till this. So A is coming, A2 is included, and let's say till the time query is running, B is also coming at 60 ms like earlier, so it will not be included in the search, right? So it's a little behind, but it's a fairly fast, and this is the default, right? Now session is what? So let's say there are multiple nodes. Session states that you will get your last write for sure. So T here is your last write timestamp, and it will be available to you from the same node. Okay, so let's say client X insert A at 12:2 like earlier. Client X search at 1 at 10 ms. So this will be available. Okay, minimal zero wait, A included for client X. Another client, maybe A is not visible to them. Okay, I mean this is basically used when you want to do the write and then read in the same flow. Okay, then that is this session. I mean, you must be assuming why do we need this. So this is the use case for session when you want to read and write in the same flow. Okay, and this is eventual. So like bounded, it's picked the slide below, it's a very behind timestamp. Okay, so let's tiny 2 node example we can understand. So a simple 2 nodes cluster is there. Strong query arrives, coordinators at T equals to now, so T is the current. Each node will serve your query must be T is greater than current. So basically all nodes will ensure that they will serve your query only when they have the data till T. Okay, and till the time query will waits. Result, all load results are view including all writes, right? So all node will give you a strong consistency with a trade-off of time. Bounded is t is now minus a small delta. Nodes are almost always, so like I mentioned, they are already in sync, so there are hardly any milliseconds lag only. Okay. Session, you insert with client x at tx, you next search any node, carries this. Okay, nodes wait up to tx, you can see your own right. So for any node you will get your right. If other client query, they might or might not get that. Okay, and eventual is a little bit behind it. So rule of thumb, if you need data across every node strong, so financial transactions or something like that, you go with this strong. Best is basically latency, so it's a mix of trade-off. So you have not trade off latency completely, or you have not trade off freshness completely. It's a blended of both, hence we go with bounded. Write then immediately read, same request by client is session, and max speed freshness optional. So eventual can be used with content sites, heavy content site where they can, slight lag is acceptable, they can use eventual. Okay, so that's it for this video. So in this video we have seen the basic Milvus setup, how can we use it, how can we use the basic vector DB. In the next video we will be checking the more complex usage of RAG, that is vector DB, a real world use case, and then in the third video we will see a full-fledged chatbot over RAG. Okay, thank you guys, have a nice day.